For the next 10 minutes, I'd like you guys all to think about antenna patterns and the shapes of these patterns and how these patterns are imported into our predictive designs. At the end of this talk, I'm going to show you guys a different way that we can model these patterns that might reduce some of the errors that we find in our predictive designs. So just to level set, I just want to talk about my definition of what I'm considering a predictive design. The designs where we're simulating the shape and the pattern that comes out of the antenna, its RF signal strength, and its propagation pattern. You have the option, if you wanted to collect measurements on site, do some spot checks to get some attenuation for the walls, and import that into predictive design. And this will help you reduce the error that you have in your design. Taking this approach, you don't need to spend as much time on site, but your design is heavily dependent on the inputs into your design. So the accuracy that you incorporate for your attenuation and the accuracy of the propagation pattern from your antenna contributes to the amount of error that you have in your design. And so the risk with predictive designs, if you don't account for accurate inputs, you may end up spending a lot of money redesigning your network after it's been deployed. Okay. So you've all worked as wireless professionals, and you spent a lot of hours of your day trying to minimize co-channel interference and eliminate from your design. So when you come home and you sit back and you relax, you think about unanswered questions of the universe, like is the glass half full or is the glass half empty? Now I know some of you have already heard this, and you've probably heard that the pessimist would see the glass as half empty and the optimist would see the glass as half full. But to an analytical mind, as a technical approach with a keen business sense, this glass might appear twice as large as it needs to be. There's a lot of sunk cost in glass that's not holding any water. Some people describe the glass as full. It's half full of water and it's half full of air, taking it right up to the brim. So it raises an important question. What are we referencing? What are we trying to compare? Are we trying to bring the water right up to the top of the glass? If this is the case, you might hear people talk about the ability to form or to displace the water and pretend that the water gets up to the brim. So you might hear people talk about the benefits of ice. Now, other people might talk about enhancing the water. If they could somehow provide you half a glass of water that could quench thirst 10 times faster, they might be able to gain some incredible market penetration. But enough about philosophy. Let's move into space, the final frontier. So some people see this as the sun, a big ball of light in the sky. To me, this is a good example of an isotropic radiator. It's radiating energy equally in all directions. So if you were to look at the top down, at the sun, you'd see energy in 360 degrees uniformly radiated. Now this is theoretical. In reality, we see something that looks more like an amoeba. So when a biologist looks at this picture, they see all different parts of an amoeba. When I see this, looking into predictive design, I see a coverage map. So instead of a cell membrane, I see my cell edge, where the nucleus is. That might be the only area with enough SNR to properly demodulate 256 QAM. I see some contractile vacuoles. These are areas of moving bodies of water in my design, some pillars that are made of concrete or metal that attenuate my signal that I have to account for. I also have food vacuoles. Now, to me, I see this as my high-capacity users, people that are consuming a lot of airtime and bandwidth, right? So I have to be careful of these users. And in this particular picture, I see a food module that's outside my coverage area. So this is a high-capacity, high-bandwidth user in a dead spot, which probably means I'll get a lot of phone calls from that user. And so what if we wanted to model our own antenna patterns and try and manipulate the shapes and maybe visualize how that pattern looked as we reviewed it across the distance? Fortunately for us, about a year ago, Wi-Fi Nigel made a blog post on his website where he did just that. He created an Excel spreadsheet where you could load the data around the 360 degrees of your circle, import that into the spreadsheet, and in one of his tabs, he'd generate the polar plot for you. And on another tab, he'd translate that into distance. So on you guys' left-hand side, you see the polar chart, and on the right-hand side over here, we see that translated to distance. Now, it's a fantastic spreadsheet, and if you go to his blog site, at the bottom of his blog post, he has a link where he actually shared the spreadsheet with the community, so you can download that and build your own maps. But the challenge here is getting precise data. If you don't provide enough points, you end up with some blocky graphs. And so if there's only a place we go where we could easily get some granular data for these channels or for these polar plots that we wanted to graph. Fortunately for us, and fortunately for everyone at this conference, you now have software where we could do just that. So once you get that software installed, if you navigate to the program directory and then to conf antennas, you'd find a list of about 1,000 files in this directory. And these are XML files that represent the antenna patterns for all the patterns within that database for that site survey package. With them being in XML format, they're text files that you can open and read. They are separated by H-planes and E-plane. We're interested in the H-plane data, which will give us our omnidirectionality. And these files have to be broken down either by degree, by 3 degrees, or by 5-degree increments, which gives us some pretty granular results. So if we combine the data from these structures with the spreadsheet that Nigel provided us, we might end up with something like this. So the graph that we see on the right is where we have the glass full of water. The signal's propagating all the way to the edge of our polar plot. And what I'm representing here is an antenna that's advertised as a 4 dB gain antenna, and omnidirectional. So here, with the glass half full, we're filling the entire circle with energy. But the actual gain, if we model this antenna, would look like what you see on the left. So only for a very small amount of time is this signal actually reaching the 4 dB gain point. In fact, there's a couple spots where it drops to -2. So we have a delta of 6 dB of gain across our 360 degrees circle. And if we look at the distance, we see our glass full, we're propagating about 86 meters. If we look at what actually happens, for a brief moment in time, again, we're at 86 meters, but we drop down to as low as 43 meters, which kind of lines up with our 6 dB delta. If we have the distance, it means we've lost 6 dB. If we doubled the distance, we've gained 6 dB. So the math works out. But we're missing a lot of space. There's a lot of error in our diagrams. And we have an error of 43 meters, right? We're off by quite a bit. What if there was a way that we could reduce some of this error? What if we took the average of all the plots around that circle and graphed that? It turns out for this particular antenna, if you were to average all the points around your graph, you'd end up with an average gain of 1.21. So we can see this is what the circle would look like if it was uniformly radiated across our polar plot. And we just compare that to what you saw before of the actual gain of the antenna. And if we look at this over distance, now this time in distance, we're radiating to about 65 meters, right? So we're within 20 meters now of our fringe cell, which used to be 83 versus 43. Now we have a distance of 65 meters radiated in all directions. So we reduced our margin of error in our design. And if someone challenged you and asked you, is 3 dB really a lot? Is 6 dB a lot? I recently heard a line, well, I guess it was a while ago, that Matthew Gast gave some advice. If you want to convince someone 3 dB is a lot, ask your boss for a 3 dB raise, right? See what the answer is there. And so take this a little bit further. What I've done with this chart is I've captured some antennas, and I tried to keep this as vendor neutral as possible, so I haven't identified the models of access points. But the first block of 4 have come from the same vendor, just different models within the family. They're all advertised as 4 dB gain antennas. But when you average all the points, you end up with that 1.21. And here I just graphed the minimum maximum distance and the deltas. So just to qualify the distance where that came from, within Nigel's spreadsheet, I was assuming it was a 2.4 gigahertz signal. I assumed my signal drop-off was -65, and my transmit power was 10 dBm. So depending on those variables, your distance, of course, changes. What I also think is interesting, on this last access point, it's advertised as a 3.5 dB gain antenna, but what we're really seeing is a normalized gain of 2.01, 2.09. But if you look at the distance, using those same inputs and variables, we're seeing a delta of 106 meters, which is a lot of error in our designs. So it might be better, we might have less error if we were to use the normalized gain for that particular antenna and keep it uniform within our graphs. So just to wrap things up, be aware that when we talk about omnidirectional antennas, they are definitely not uniform in all directions. They do, in fact, look like amoebas. If you want to account for that design, this is one approach that you might want to take, where you average the gain around your polar plot. It also gives you some insight into the characteristics of the antenna. It gives you some idea of the quality of the antenna. The closer they get to having uniformity around their polar plot, the better off the antenna design and the better it'll perform for your network. And this is also, because of the variable, one of the many reasons that you want to validate your design. So always, always, always validate your design once it goes in. And if you have any questions or comments, once again, I'm Troy Martin, and you can hit me on Twitter @TroyMart.